Alright, I still need some time. I'm about halfway there.
Living on a prayer?
Yeah, absolutely. It's a work in progress.
I thought this was group reading. We all take turns reading a paragraph out loud. Yeah.
Alright.
Yeah, I have another question. Um, Dyson Sphere, Dyson Sphere is basically energy source based on electromagnetic field, right? It's not a plasma based, like.
Well, I think there's a couple of versions of it. Like,
Oh, I see. Mhm. Oh, okay.
there's also... Go ahead.
It's like an ecosystem. Oh, I see. What is? I see.
Yeah.
The energy source of Dyson Sphere.
I was just gonna say I referenced the Kurzgesagt video. I sent it in the thing again, just as like a thing. I didn't, like I said, get through this paper, but one of the things he did mention about having a rigid body like sphere around the sun wouldn't necessarily be the physics of putting it up there, but the um, of being hit by like asteroids and other space debris. That would be the biggest issue because we want to keep this as durable as possible for as long as possible with doing the least amount of work to it. So inside the video, he said instead of a swarm, like you said, it would be a ring, but basically cross sections of a three-dimensional sphere put together. So it would give it some pliability, which would, obviously, if there's spaces and gaps, then there's less chance of it impacting a whole area, rather maybe just one solar collector.
Wait, so, Mohammed, what's your take-home point from that?
Take home point was that having a physical large sphere would be not plausible, but would be more plausible. I was just adding on to Jeff's point was that um, having like a ring or three-dimensional array of rings would be better.
Okay. I feel like on that note, we can go into this author talks about 3 ways in which their Dyson spheres would be unstable.
Okay.
So, you want to just jump into the math if everyone's up to that? Yeah. Okay. So, I mean, I can read it just for like, I don't know, just for like background noise. But it is often asserted as by Dyson, for instance, that monolithic Dyson spheres are impossible or unstable, but rarely it's as carefully explained. Here we illustrate 3 ways in which they would not be stable. First is gravitational non-stability. So, first illustration of non-stability of a monolithic Dyson sphere can be deduced from Gauss's law, as described by yada yada yada. Consider first the potential inside of a uniform empty sphere, whose material exerts a force following a radial inverse square law. All right, so that makes plenty of sense, right? For instance, because there's a charged insulator in which case the electric field generated by a bit of the surface with charge U is E equals Q r hat over r squared, or massive in which the gravitational field generated by a bit of surface mass m is. So when it says the potential inside of a uniform empty sphere, whose material exerts a force following an so it's basically saying everything around that sphere is going to be acted on by that force, electromagnetically and gravitationally, right? Right? Nothing too comp. What about outside? So why is there a negative for that G? You know what I mean?
I think that's just general, like, semantics. It's an attractive field, so it's negative. That's usually what goes
That's
on.
saying that inside the sphere you'd be going towards the center, right? It's saying it's weird. It's saying like if you're going inside this, like yeah, it's saying right because radially is outward. It's saying if you're inside the sphere, the gravity would be pushing you inward.
let me see. That sounds right. I just want to double check.
Electric field is outward, and the gravity is
Field generated
inward.
by a bit of surface with mass m.
Hey Tim, do you see this paper? Is it referring to the
Yeah,
force within the sphere or or once you're outside the sphere?
the R is the field point, right? It's depending on where you pick it up. You could pick it up
Gravitational, I'd
outside.
say, is definitely inside. It's not
Yeah.
talking about outside.
Are we talking about the force on the sphere, or we're talking about
inside? There's
the
no
field
charge.
point?
We know that. It's insulated.
Well, it says the potential inside of a uniform empty sphere.
Assuming
Material
okay, then.
exerts force following a radial inverse square law.
He
Okay.
even said it's elementary to show Gauss's law implies that the inside sphere there's zero field, and outside the sphere can be treated as a point source. Since it does not exert any force on particles inside itself, by Newton's first law, particles inside the sphere exert no force on it.
So it's outside, right? The field point has to be outside.
Yeah, Jeff, you seem a little silent. What are you thinking? Okay, so we're all a little confused here.
The R vector is really field point subscribed with the source point.
Yeah,
it's saying if you have a sphere, like on a galactic scale, like on that kind of scale, any particle near it will have a negative, right?
it will have an attraction to it.
Gravitational force will be directed negatively radially.
Yeah, so it'll be coming inward. So yeah, it will be attracted towards the center. Yeah,
It's saying, imagine you have stuff around this sphere. Things are going to be gravitating inward towards it.
Which makes sense if you're. Sorry. I was even go about it to say that it makes sense if you put such a large mass into the space, then it will contort the gravitational field, so anything around it will be attracted to it. Same as the amount of pull. Well, not same because the sun is very dense, but you get what I'm saying. Like same sort of gravitational pull around, so it will be pulled in. Hence the negative. If there's a point that's outside, it's getting attracted to it, so it's getting radially inward, which makes it negative. Anything that's inside as well will also be directed downwards to the center. Same as like we're on Earth. Our gravitational field gets directed to the center of Earth. That's how we stay upright.
Okay. Cool. So I think we're good to go to the second paragraph. It is elementary exercise to show that Gauss' law implies that inside the sphere there is zero field, and outside the sphere can be treated as a point source since it does not exert any force on particles inside itself. Newton's first law: particles inside the sphere exert no force on it. Okay, so interesting. So is it saying the sun exerts no sphere on no electrical force because the potential
inside there's
is
no
zero.
charge. Yeah,
Mhm.
zero. Potential zero, electric field
Right.
zero. Yeah.
Mhm.
Mhm.
Yeah. Yeah. It basically seems like a
Yeah.
grounded.
Well, if you put a charged particle inside there, it would start acting what's it
Mirror
called,
charging.
as an attraction for any other
Oh
particles.
yeah,
So
because of the mirror charging particle.
where am I going with this? Sorry. hold on.
Can you guys hear me?
Yeah, we can hear you.
Oh, okay. Yeah, right. Because it acts like a grounded sphere. So if we put the negative charge on the near them, it's gonna have induce the positively
Yeah, I lost my
induced
train of
charge
thought.
on the ground.
Sorry.
Oh.
That's what I was thinking too. Like if you
Induced
start with I don't know what you call it.
mirror charge. Right. Hmm. Oh, you're talking about concentric two spheres between.
There's no charge inside the sphere. There can't
Right.
be. If you put a charge inside the sphere and it's moving, then that in itself will generate an electric field, and that wouldn't be possible if it's insulated. So there wouldn't be a charge inside. It's a charged insulator, meaning there's a surface charge, not a volume charge.
Mhm.
Yeah.
There's no electric field on any particle inside, so there's no
The
electric
potential
force.
is 0.
Mhm.
No potential.
It's-
Yeah.
Right. Okay. Cool. Um,
Mhm. Wait, is it two-dimensional or three-dimensional? Is it 3D, right? 3D, okay. The surface area. Mhm. 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 Right.
hang on,
Mhm.
Jeff. You were going way too fast. Like, bring break it down. What? One more second. One more time. So dA. Hold on. dA. Are you reading right now or talking? You're talking. You're telling me to consider a particle at point S. Okay. So go ahead. Yeah. Um, and dA is from basically from B to what is dA?
Small amount of area.
Oh, I see. It's like okay, I get what you're saying. Okay, it's like it's a little linear, right?
Ring.
It's like a little
Isn't it?
strip. It's a little
Isn't it
strip.
supposed to be? Isn't it supposed to be
Like
r
a washer.
squared
Think
sine
like a
squared
washer in
theta?
calculus.
Yeah, isn't it supposed?
A
Isn't it
washer?
supposed to be?
Like a disc or a washer when you're doing integrations? Like a very, very
Right.
tiny.
Isn't it supposed to be? Isn't it supposed to be r squared sine squared theta, and then you integrate over d phi? Shouldn't that be dA? Because it's a pi r square, right? d phi,
Oh well,
dp,
theta
right?
goes from 0 to 2 pi, right? So
Depending on the point S.
In this case, yeah, I guess theta goes.
like I think, correct me if I'm wrong, but I think the way you get here
Yeah,
is
Yeah.
it's a dp.
Theta is
Yeah,
0
you have to
to pi,
integrate over
and phi
dp.
is 0 to pi. That's how they're doing it.
everything's
Yeah.
kosher. Good. Okay.
Everything's
Mhm.
kosher.
We're
Did you
just
get a
rearranging
rabbi to
variables
double
here.
check though?
What's
That
that?
makes sense.
I said, did you get a rabbi to double check though if it's kosher?
I mean, I think we're good. I think this is a good consensus truth. So okay, so we're all in agreement how we're calculating dA.
Yeah.
So then it's saying, right? So there, that X is kind of throwing me off, but whatever.
From the x is the distance between the origin to the particle at point S.
Okay. So Jeff, keep going. Right. Then the X direction is cosine theta.
Yeah.
So
Track.
does he?
No, the vector y should be positive, right? Because we have it's inside of sphere, so it has to be positive left.
Is Tim talking?
But yeah,
I can't hear. No.
you can't hear me. Maybe it's my earphones.
I can hear you and I can hear Isaac. I can't hear Tim.
How about right now? Can you talk? Can you hear me?
I don't think I changed any setting. He's not muted. User volume is max. Show non-video. Yeah, invite to server.
Okay, let me just
Hold
go
on, hold
change
on.
my output.
Tim, say the first 5 letters of the alphabet.
E,
Oh, say the
Can
first
you hear?
5.
A, B, C, D, E.
Oh, did you hear that?
No.
Alright, that's messed up. I don't know what's going on.
This entire time, I have not. I didn't even realize he was participating. Can you hear me?
Yeah, I can hear you. Let me just really check this the
Wait, Mo,
Discord
maybe
meeting.
I mean this very intellectually.
Uh-huh.
Log off and log on.
Yeah. Give me a second. Okay. Let me. Okay.
Say the first 5 letters of the alphabet.
How about right now?
I can hear now. Beautiful.
Nice.
Science. All right. All right, Jeff, let's get focused here. Or do you need a... All right.
Nice.
So
Sorry.
basically, we're saying if a particle, saying electromagnetically speaking, if a particle is distance s away from O, it will experience a force Fx equal to this. Okay. C depends. Okay, so I'm going to pick up after equation 5, where C depends on the nature of the force. By symmetry, force in the y and z directions must be 0. Why is that the case?
Mhm.
Oh, because it's only moved in the x direction. Oh no, that I follow. Okay, where C
I'm sorry. Where's B prime?
he just made it up.
Okay. Yeah. Okay.
So I'm gonna take a screenshot real quick of this before I so we have something for all right. Oh, you don't have this. Whatever.
I thought we were taking a group picture.
No, I just took a snipper. Unless anyone has whatever. We'll do it at the end. All right. Just thought that would be good. All right. Download, save. All right. Well, we'll take some good ones at the end. All right. So we were saying symmetry, the force in the y and z directions must be 0. Dropping a perpendicular onto the radius OS from B. OS. Dropping a perpendicular OS from B. What is that? No, I actually. What is it's Jeff, move your mouse again. Yeah. Oh, so it's basically following the DA line. Wow. Okay. So it's saying gives and using equation 2, get r cosine theta equals r cosine phi minus x equals r squared, big R squared minus little r squared minus x squared over 2x. Right. So then there's what do they do with the cosine theta? I don't know.
Cosine phi. No, that whole thing is r cosine phi. No, not at all. I was sprouting monkey business over here. Ignore me.
All right. So what's the upshot here? They're saying so they're basically calculating the distance from S to the edge of the sphere. You see. So r cosine theta is the I'm just writing these for myself. So distance S from surface, and distance is already traveled. All right. So what's the upshot here? We have r cosine theta equals that, and then
It's basically finding a force at x, right? Yeah. Because x is the time dependent one, we can treat as a different variable later.
so right, where do we get all these terms from? Yeah. R comes from equation 4. Okay. Mhm. Okay, so where, hold on, dA equals 2 pi r squared. Okay, so where does that big C come from? Okay, so basically they substituted for dA, dfx, and r cosine theta. Oh yeah, okay, fine. Say that again? Oh, okay. I mean, they didn't write a constant in the solution, or yeah, that's what I'm saying. It's definite. Okay. So anyway, that equals that whole thing. So it comes out to 0. Oh hell, I could have said that. It's fucking it's what do you call it? Symmetric. It doesn't. Thus, in the case of gravity, a perfectly spherical and rigid sphere experiences no net force from a star interior to it, regardless of whether it is centered. As we will see, it will experience utterly destructive differential forces. This means that the center of mass of the sphere and the star are gravitationally uncoupled. So there's no reason for the sphere to stay centered on the star. You can say it is neutrally stable. That is in an equilibrium configuration that's neither stable nor unstable. Practically, the non-stability of a monolithic Dyson sphere means that it would require active station keeping to prevent any perturbative force from causing it to drift into the star. There's only the symmetry of the sphere that led to this result also means that deviations from sphericity would result in an unstable configuration. So I think basically what he's saying, the moment the star or the sphere move 1 centimeter, the whole thing, like,
Will collapse in on itself.
yeah.
Yeah.
And in English, why again?
Yeah. Right.
If the star moves, there's no force to move it back in the x direction. Why is there no force?
Yeah.
You would need a propulsion or something to stabilize.
But also, we are assuming the mass is homogeneous, right? In Yeah, right. And if it is not homogeneous, you cannot make perfectly, aligned mass distribution on the sphere. This, yeah. Mhm. Okay.
Hang
Right.
on a second. Hang on a second. What it's saying is, I got to think out loud a little bit here. Say that again? No, I'm gonna think out loud and then you tell me what I'm missing. Okay? It's in equation 7. It says basically it's saying whenever it moves, there's no force acting on it, the x direction. But then why were they saying the y component and z component forces cancel out?
Just imagine it moves in the X linearly, right? So the star and the sphere, whether it's rigid or non-rigid, they're not coupled. So if either the star or the outer shell moves even the slightest bit in the X direction, right, that equilibrium is going to get thrown off. When that equilibrium gets thrown off, there's nothing stopping that sphere from coming into the large gravitational pull of that star. So even if you perturb it just a little bit, say an asteroid hits it and it just causes a little bit of damage, that's going to cause such a slight perturbation that's going to throw the entire thing off
I
of.
see what you're saying.
Right.
So what we're not saying. So, long story short, as long as you have just the sphere and the star, in that situation, all the forces will always cancel out in every direction, right? So as long as there is nothing around this sphere and star, it's safe. But as soon as a single asteroid moves at any distance,
Not even if the asteroid moves it necessarily, but even if the star goes around in orbit, right? Not necessarily that the sphere will follow a perfect orbit with that star,
I
right?
see what
Right.
we definitely can't. Definitely can't.
Right. I think the
Just
better way to make this sphere work that you have to make a ring, I think. And somehow this ring has to purse out the radiation pressure onto the sun so that it can sustain the sensor.
say that one more time.
But I think it would be much better to sustain ring rather than sphere because sphere is such a large object. But a slight changing in distance would collapse it down. The ring would be best way to cultivate that energy. I think sphere is like
Well,
maintenance fee is going to be really ridiculous.
I think what you're saying is I think what you're saying is it would be less of a colossal catastrophe if the star or ring moves a little bit as opposed to if the
Right.
star or sphere moves a little bit. There's
Right.
more there's less magnitude of mass to worry about if it's a ring
Right.
versus a sphere.
I mean, I'd
Right.
say even if it's a ring, right, a slight
Mhm.
discrepancy in change will still cause it.
Right. So I was thinking maybe they can generate the electromagnetic pressure towards center down to the earth, the sun. Maybe it can maintain the distance. I don't know.
Yeah,
How would
just
you how would you direct the radiation pressure inwards?
Um,
If it's emitting outwards, then it's causing a pressure on the inward side of the ring. If that
well,
makes sense, unless I'm wrong.
yeah. Maybe I was thinking about like coming from the ring, like
Uh-huh.
a laser beams toward the center of the sun,
I
and
see.
uh, like each side of the ring, the sending electromagnetic pressures to maintain the distance.
So that beam that would point in would counteract and
Right.
act as a stabilizer. All right, that makes sense. I like that. That's cool.
Mhm.
Tim, make your point one more time.
Um, Basically, what I was thinking is that to center to locate the ring exactly on the center, so we're sending a beam from the ring toward to the sun, which is electromagnetic pressures. So you can maintain at the exactly around the sun. Right. We could do that, but that would be much hard to control. I think. I don't, right. Well. Right. Right. So I was thinking maybe we can use the sun's energy to creating electromagnetic pressure uh, onto the sun. So like ring can move around these like on the centers. Like they go ahead. Oh yeah, what I'm saying is that if we can generate from the ring to shoot down the center of the Earth with electromagnetic pressures, maybe ring can relocate the impact center as it perturbated.
I guess, Tim, I'm not guessing. I can't tell if you're making a general point or like a more technical point. Like right now,
Yeah, I'm technical point.
you're
It's more like a
right now. I'm
technical
just
point.
saying offset any change in location with electromagnetic pressure. So you're
So if I
saying
can, sorry.
use like harvest the sun's energy, put
Mhm.
pressure back on this to like relocate the sun or relocate the ring.
The ring,
So
yeah, the ring to
if
be
I could
relocated.
interject real quick, I think what he's trying
Mhm.
to say is that so when the sun is spitting out its electromagnetic energy, right, those particles cause a radiation pressure, right? That radiation pressure can move that ring, right? So what he's saying is if this is the star and it uh, has an infinitesimal amount of pressure that dislocates this however much, if you shoot another laser beam back into it, the radiation pressure will be counteracted by the pressure that's being shot out. So no matter how much, it'll come into equilibrium and there won't be any perturbation,
But that
at least
doesn't
from the
solve.
radiation pressure.
But you have to then like do that even more so, shoot even more so into the sun to counter, to like rebalance anything gravitationally. You get what I'm saying?
Right.
And that Yeah, and that's exactly what I think his point is in the paper is that you have just looking at it gravitationally, you would need a restoring force to ensure that there's no perturbation. Right, that's a good point. Yeah,
I'm
that's
just,
big brain moves.
as I understand it, it's saying forget gravity for a second. You need electromagnetic pressure to offset. You need electromagnetic pressure from the ring to the sun to offset the one from the sun to the ring. And then even more so, you need it to offset any gravitational ramifications once they're not like concentrically at the same center. Right?
Yeah, I think that sounds right.
Okay. All right. I mean, on that note, let's go to 2.2. Yeah. All right. Does anyone get that sentence with an additional cosine gamma term to account for the projected area of the element area? Does anyone know what that means in English? Like, I don't. Pictorially? Okay. Force divided by area. But yeah.
Uh,
Okay. 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 Okay.
I
I
I'm not
think the
sure if the
gamma is up there. If you go up there, like there is a circle that has a gamma is an angle. Yeah, you see the gamma.
Uh,
Yeah,
I think that's meant to be like a scattering angle, like the scattering,
scattering
the
angle.
quantum mechanical scattering effects. So that gamma is like just where it could go.
Oh,
So that's why. you
those
need to
are
take
the
into target.
those are the radiation. When the radiation hit the wall, it's reflecting back to the center.
Yeah.
All right, Mo, you understood what he said, so you can explain it to me.
Yeah, so he's talking about the radiation pressure. So when it shoots off from that origin point, right, and gets deflected back, so you can think about the big R as initial and then little r as reflected. So that gamma is the angle between the incident and the reflected beams.
Oh, it's like back to optics
Yeah,
almost. Freshman physics. Okay.
if
Wow.
I understood Tim correctly.
No, something doesn't seem right. Something doesn't seem right.
Let's see this again.
All right, I'm gonna go off camera. Let me think if I can think of it.
So it's the projection of that reception. So maybe reflection isn't the right term to use, but yeah. Projection involves two vectors. Projection is the intersection between two vectors. I think yeah. Yes. No, because gamma's coming from the top down, not from. So
Well, like we
gamma.
can think of. Oh, sorry about that. We can think of
No.
the gamma. We can set the gamma equal to 0, right? And that means that the radiation going along the x-axis is going to reflecting back, and then that radiation will be also conflict with another radiation coming in. So I think the radiation being accumulated at that point, and that's why that is the highest force acting on the along the x-axis.
All right, let's take our time here.
Did you link that? The Stack Exchange. Thank you.
The pi r square is the area the radiation going through, right? In our case, the area would be a little bit different.
Pressure force should be larger. Reflecting. Causing gamma turns to intercepting the photons within. I think I still stand by that. Maybe scattering is the wrong word, but it's definitely talking about the radiation pressure getting projected back onto the source, and uh,
I'm trying to Google on my own while you guys are doing this. See if in parallel. It looks like it's something about photons themselves.
I have a cat.
Tell them to I'm joking.
Why was he yelling in the background? He's a little horny these days, so he can't keep his mouth shut. Yeah. He goes around harassing everyone. Just from the stack exchange you sent, someone said you will get the right answer if you represent the plane wave by a beam of photons using the relation between energy and momentum, E equals PC, and setting the density of photons in the beam to match the intensity of the wave. Since reflected photons apply more momentum transfer to the surface than absorbed photons, the pressure force should be larger on reflecting surface. So, yeah. Yeah.
Hmm. First, cosine theta comes because the area of the cross-section of the beam is incident on the surface is a cosine theta. Second one comes to component force. So there's two cosine thetas? Honestly, this explains it pretty well. I mean, in my personal humble opinions, let me put this in the chat.
Yeah, the cosine gamma is the radiation. But when the photon conflict each other, there's higher pressure.
Do you have access to a computer or no? Or you
Right
just
now,
on
I
your phone?
can't.
No?
Yeah, I
Okay.
just have to use phone right now.
Okay.
I'm actually in the cafe. I can do that in 30 minutes.
Okay.
I
I
think
mean,
you're right.
it says with an additional cosine gamma term to account for the projected area of the area element intercepting. Say that again? Oh. Okay, but we don't know why. Still don't know why it has that cosine term, but we'll figure it out later.
I
All right,
think
let's
that's
just keep going till 10. So, Steve,
right. 3 is the change of variables. Yeah, 3 is we had R and then they did RDR. 6, yeah, goes back to R cosine theta. Yeah. Onto the line containing SB. So that'd be like X or X prime, right? Watch your profanity. Alternate interior. No, gamma would. Yeah. Gamma is between O and perpendicular to O.
That's what they said, right? So what? All right, Jeff. I don't mean to cut you off. Just bring it home. What are you telling us here? Okay. So little r cosine theta plus, little r cosine theta plus r equals r cosine gamma plus little r. Right. So little x cosine theta plus r equals r cosine gamma. Right. I need some of my own time to like look through those angles, but follow what you're saying. So now, do we understand why that cosine gamma term is in there? Or still no? Okay, fine.
Yes.
I think I don't know. I mean, there's two things here. There's like calculus and there's
Yeah, I
geometry, right?
understand it.
Uh,
They came to the same gamma, right?
Say that again.
They're the same gamma, right?
You got the same gamma.
From the other P diagram.
It's the same gamma from the diagram. Right?
Okay.
All right. Jeff, you seem to be on a roll, so just take it away right now. So it's interesting what they're saying here. What they're basically saying is that they're talking about as it sends photons out. It's almost like putting a thrust on itself. Is that what they're saying? Let's read the last two paragraphs of 2.2. Where do you read that? Hang on a second. Hang on. I'm scrolling. Right, I'm lost. Where is 2.2? Oh, here we are. It's here. Yeah, but read on. Like, read the last two paragraphs. Remarkably, this result extends to any shape, completely surrounding the star. Dot dot dot. No, I think it's saying something else. I think it's saying F sub x from any photon is 0. Like the force from any photon is 0. Oh, but I think Mo and Tim, back me up on this, but or back whoever's right on this. He's not saying it's 0 because of symmetry. He's saying any photon puts 0 radiation pressure and 0 force on the sphere. See, it says, and so even at the end of after equation 11, it says, and so even with this cosine gamma term, the sphere still feels no net force.
It is by symmetry, though. The next line, the line after the next says it. Oh, I see. Okay.
So then why would it extend to any shape surrounding the star? Like, you see, he's saying remarkably. Why is that remarkable? And why do we know it's true? Like, what is remarkable here? What, and how do we know that with the math? Meaning, what if it's not a symmetrical?
Okay, so
I
what it's sorry, what it's saying is whether it's a square, a triangle, an ellipsoid, whatever the case may be, that amount of radiation pressure, it'll be evenly distributed across the entire thing from the sun.
Oh,
So
it's
that's why.
not. So then in that case, why does it say remarkably the result extends to any shape completely surrounding the star? Why not any symmetrical shape?
To see the result. Okay, sorry.
Oh, but you get the difference I'm making? Meaning, if the shape was like some shit like this, and then, smooth semicircle, you're going to explain that now? You're going to explain why it applies to shit show shapes. Right. Okay, go ahead. Is it saying because sort of like the source? You know what I mean? Like any area you enclose the star within, net momentum will be 0 from symmetry. Mo, are you following this?
Kinda. I think so. Um,
Is that a separate argument from what we just calculated mathematically? Does equation 11 show that? What is equation 11 saying? Oh, so he's making a huge jump then. All right, let me read it one more time. Jeff, just hang on a second. Okay. Equation 11, he shows how it's applicable to a sphere. That's part A. Okay. Then he says, remarkably, this result extends to any shape completely surrounding the star. So any shape is symmetrical or non-symmetrical. And he says, to see this result another way, consider that by symmetry, the ensemble of emitted stellar photons has zero momentum. And so any shape that absorbs them, all of them, will not gain any momentum from them. Well, shit, then he just wasted our time with equations 8, 9, 10, 11. Yeah, I guess. But they're such, you know what I mean? They're such a, like,
I think
they're
you're
not
getting caught up
nicely logically
between.
linked.
I think you're getting caught up between the spherical symmetry of the star as opposed to the spherical symmetry of the shell. It doesn't matter about the shell because as long as the star is spherically symmetric, it's going to give out the same radiation pressure.
So is he saying, right? No, I get that, but is he saying this equation 11 on another shape? Is he saying it would come out to zero or not?
Yes.
Would equation 11 come out to zero for a box or not?
Yes. He says, remarkably, this result extends to any shape, completely surrounding the star. Assuming that that box is surrounding that star, it's going to be zero.
Jeff, you're saying the calculations come out to zero either way? Why do you think so?
Yeah, R square cosine theta is the area. R square is the thing is also coming back to the Gaussian surface, and because there is no potentials, and we can say that there is no charge nor the radiations, right?
What is Tim saying exactly? There's
No, what I'm saying is that we enclose with the Gaussian surface, and the charge densities, the charge is not there, and for the radiation case, each photon has a momentum, but if you enclose any surface, the sum of momentum has to be equal to 0.
yeah, you're just saying it's uniformly projecting out the photons.
Yeah, because if we assume, right,
All right, forget what Isaac is saying. Let's just read these last two paragraphs. Move on to 2.3.
oh yeah, that's it. That's it, yeah.
But I think. Go ahead. Go ahead, Jeff. I think what he's saying is, correct me if I'm wrong, what he's saying next is when the Dyson sphere sends photons out, um, then there's nothing to counter it. You know what I'm saying? It's like a thrust on itself. Like inside the sphere, the momentum is 0, but when it sends photons out, now there's a thrust it can't account for. See, so read the last paragraph. This exercise does reveal an interesting caveat, however. Allowing stellar photons to escape from the Dyson sphere, or preferentially, yeah, and or be preferentially re-emitted from the outside surface farther from the star, could provide thrust that would recenter the Dyson sphere on the star. Hold on. It's an interesting. It's a very. It's a very interesting theoretical argument. Just let me think out loud for a second. Whatever. How do I put this? I don't know, Jeff. What do you understand the last paragraph to mean? Oh, just what does the last paragraph mean to you?
For that case, the photon pressure on the sphere is 1/3 of the gravitational force. The photon escape from the sphere, and the pressure that we're affecting on the sphere is 1/3 of the gravitational force. 1/3, yeah. I did calculate it out from GR class.
So why what's
The photon energy densities has a gravitational pressure that is equivalent to 1/3 of the gravitational force of the mass density.
Jeff? Can you translate?
Yeah, that's right. That's right.
Can you translate? Can you translate, Jeff? Yeah. it's still gonna neutralize out to net zero. Yeah. I don't know, or I have like this like vague idea, but to I don't know how to. I guess I'm just saying it's surprising we thought of like we thought of like we didn't think of sending photons out to readjust the sphere. Rather, we're like, oh, let's put electromagnetic pressure on the star to readjust, one of the two. Yeah. No, that's the idea of Dyson sphere. Like certain photons have to escape. All right, it's fine. Let's move on. All right, I think this is good enough for the last section. Then we'll just like talk a little bit. But yeah. All right. Can I skim it first? Give me a sec. I'm still reading. Yeah. Oh, it's interesting that they have f here. They have the derivative of on m, not v. Right? It's usually f equals m dv dt. But they have the derivative of it on m. Oh, cool. Right. So what is the formula? What the heck is the formula for power again? The df dt or no? Yeah.
Work, isn't it work over time?
Yeah. Makes sense. Work over time. Okay. That makes
It's the
sense.
same as force times velocity. So it's mv, velocity in this case is also mv, right? Because we're talking about the mass changing, using the mass to as thrust. So it's basically just mv times mv, and then it's half mv, I guess, for what the hell is that thing called? Symmetry.
Mhm. Yeah, there's a lot. So anyway.
Hmm. The nearest star, more importantly.
Let me see the little. Oh, I mean, what? I mean, yeah. Well, yeah, I mean, I think this section is overly both complicated and simple at the same time. All it's saying is it'll put a force on itself to counter any perturbations with, you know, a derivative on its mass. Okay. All right. Is everyone okay with sorry, Jeff, finish up. Yeah. Right. I don't know. Anyone else have any? I feel like this is the time where we can all like kind of wind down and our heads kind of hurt a little. What does everyone else think?
I'm
Think
pretty good.
you
Yeah,
guys
I'm
are
good.
good.
Yeah, I'm
All right.
good.
In that case, I mean, I'm gonna stay quiet for a little. 'Cause my head kind of hurts.
That's fair.
So where'd my video go? Where the heck did my video go? Oh. All right, you guys can keep going.
Hmm.
I'm just listening along. All right,
Yeah, I'm
I
good.
don't know. Okay.
But also we can think of in terms of the center of mass changing, right? Oh no, never mind. Go ahead. Oh, I see. Mhm. Yeah, right, right. Yeah, I'm good. Absolutely. Mm. That's good approximation. Yeah, that's good approximations. Yeah. Yeah, makes sense.
I mean, I think the upshot is that it'll be unstable in terms of it has a life to it, right? It's constantly decreasing in size. So interesting. It's like a star, basically, right? Yeah. Haha.
I hate arbitrary units. I was thinking Armstrong units, but that wouldn't make any fucking sense, so I don't know what else AU could be.
That sucks.
But wait, there's more. Bill Murray wrote this paper. Are we continuing into the section?
What are they saying? Oh, are you saying the star is gonna bring the sphere gravitationally inwards? Okay. Wait, what are the two scenarios again?
Right, that can be solved
Right.
by spinning around. If you spin the if you spin the Dyson spheres, you can solve that problem.
If you what?
Mhm. Oh yeah.
You did mention centrifugal forces, centrifugal in the second part.
I see.
Yeah, imagine the amount of freaking energy you would need to make a centrifugal moving thing around something as dense as a star.
Yeah, that's why the yeah.
Yeah, but
um,
it's not about the air. It's about, I think it comes down to again overcoming that huge gravitational pull. You know, like you would have to have a force, a spinning force strong enough that inward gravitational pull just turns into allows you basically have to get past the exit velocity, quote unquote. Yeah.
Right. But that's why the venue would be more efficient. Yeah.
Okay, so what's the summary of this argument? So what again does spinning do? Yeah. um, no, I get it, but where are you going to get that energy to keep accelerating it that way? Why is the centrifugal force at the pole zero? Oh,
You
the
can't
north and
spin in
south
three
pole.
directions.
Okay. Um, I hear, yeah. All right, yeah, okay, so rig makes more sense. Yeah. Okay.
Wow. Graphene. I don't know carbon versus graphene. Let's see. Carbon is a chain linked in the double rotating, so it's more like a rope. Oh, okay. Damn. Yeah, that's pretty fucked. Carbon-carbon is not the strongest bond. Hydrogen bond is.
Yes.
Yeah, hydrogen is the strongest bond you can have. Hydrogen bonded with nitrogen, oxygen, or fluoride. Those are the strongest bonds. No, so carbon-carbon would be the two carbon atoms linked, and then you'd have hydrogen surrounding the carbons. Yeah.
Wait, let's look at that footnote for what does 8 say? I'm curious.
Yeah. Bulk modulus is just talking about the density of something.
Okay.
10 to the eighth is like what 100 million, and then 10 to the 19th, or 10 to the 14th. That's five, or that should be 5 orders of magnitude higher. What's clear? And so it is 19 orders of. Because even the carbine is 9 orders of magnitude not strong enough. So 9 plus the 5 does not give us 19. Okay, 5 should be 14. The density of such material is 10 to the 14th times higher. So, oh, okay. I see. Yeah, that makes sense. There we go. That makes sense. It's denser, but
But
not.
then the problem is that if you make it denser, then the mass increases. So the whole equation will change. Mm. So the yeah, exactly. So it's impossible to make one. Yeah.
Summarize the argument one more time.
Yeah, that's pretty hard.
Okay.
Well, I
So you
think
need
there is a
more orders of magnitude to keep it together. Got it. Got it. Got it. Okay. All right.
I think the orbital megastructure would be much better to harvest in the energy, right? Yeah, like if you orbiting the megastructure around the sun, it would be, I guess it would be much more efficient. I guess I don't know. Well, like a flat surface orbiting around the sun, I guess.
Like a
Mm.
disc,
Like
like a
yeah, let's say like yeah, like a square, like facing the perpendicular to the surface, facing at the sun instead of orbiting around, and we can harness the energy. In fact, they can locate right next to Earth. Actually, if you can build up um, right next to Earth, and it's just following as Earth is rotating around the sun, and the screen cultivating energy. Oh, hey guys, can I come back like in 5 minutes? Okay.
Oh,
Yeah.
Are we
yeah,
guys?
let's talk as guys for a little bit about just what we want to do next time, and then if Tim doesn't come on within like 10 to 15 minutes, we'll just
Bye
film it.
guys. See you guys later. Okay. Okay. Yeah. Yeah. And
Oh, we're taking a. I look good,
bye. All right. Have a good day, guys.
Suits him.
Tim. All right, let me add Tim to the group.
What's up?
Um, how do I add in a group? 1 second. I just care if I look good. I mean, I know I'm being okay. Where the heck? I have so many tabs. Okay, here we are. I posted in the WhatsApp too. Hold on, did you post it?